All right. And I realized that I was just going to put everything on the electromagnetic grid and see what happened, right? And I realized when I put everything on electromagnetic grid that belongs on the electromagnetic grid, there was nothing left except for gravitational waves. Not gravity, just gravitational waves. And because we were always taught it was a shock wave going across space. And, because we got the metric, right? Well, if you get rid of the metric, all you got left is an EM field. And there's an EM field out there, but it wouldn't be a shock wave. So I'm going, how do you shock nothing? How do you shock space? You can't. But when you think about the fact that neutron stars and black holes and all that stuff are big, spinning electromagnets. They generate massive electromagnetic shells around them. And when you recognize that the EM field is everywhere, and these things are big generators of the EM fields. I mean, huge generators. And what they do is when they're spinning around each other, they're literally broadcasting. They can't make a sound because they're in space. So what they do instead is they make a visual sound. They grab onto the only thing they can and they transmit from there. And that's why the shock waves of large spinning bodies become big light waves. So LIGO just recorded 2 neutron stars that did this. And they did the math for it ahead of time, and they did the math for the light that was going to follow in the whole 9 yards, and they sat down and they tested this, and 1.7 second delay for the light. The black hole, the big shock wave showed up first. I mean, these things are huge waves. They move atoms, was it 100 and something million years later? This shock wave that hit us that LIGO just did was 100 and something million years in space. And it shows up here and it's still shaking mirrors and stuff. Tiny, 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 tiny little bit. That's why they need to build these huge lasers to test it. And they got to surround the laser and everything and protect it in a vacuum and all this other stuff. And God bless them for it, because they're able to literally read the gravitational waves that are hitting Earth. And I'll tell you what direction they're from and stuff like that. Maybe not know how far, but in this case they knew it ahead of time. But the point was, their math for the gravitational wave involved I call it a tax. It's a little wear and tear as it travels for 100-something million years through space. And it actually lowers the frequency. Just a little bit. Just a huge wave. And but if you look at Einstein's math for light, they don't do that. What they do instead is they say, okay, well, at that distance there's X amount of expansion, so it's going to have this much redshift, that much reduced in the frequency. And they're just literally pre-measuring it and pre-calling it expansion. So I pulled up the Russian version with Noether. I love Noether. If you don't know who Emily Noether is, look her up. She's awesome. Mechanical realist. And after the whole big split there in general relativity, the Russians took off and made their own system. And all of this stuff that we're having problems with today in general relativity, they have no problems with at all. It's called mechanical realism, is really what it's called. And what it is, there is when a light wave goes up, like a galaxy, all right, or a sun, and it radiates out in 360 degrees, right? And so when it goes out, over the course of time, it thins out and thins out and thins out and thins out. And we account for that. What we don't account for is it doesn't just thin out. The wavelength over time slows down until it becomes, right down there in the CMB, that background radiation. When it gets down that low, we can't really hear it anymore. It's there, it's floating around. It's just background noise at that point. And when we look out our telescopes way out, we see it, and we call it the Big Bang, or the leftover from the Big Bang. But the end result is everybody but general relativity realizes it, that over time, massive amounts of time in space, like 14.5 billion years, there's not enough signal left to give it an actual. Instead, it's just kind of like weep, and it's weak, which is why we have to look in the deep redshift on our telescopes and stuff, because there's almost no signal left, and what there is long gone from the human eye. Like, we can't actually see those stars out there. We need special equipment. And so anyways, yeah, that's what I found out today was on the electromagnetic scale. What's going on is these shock waves aren't, well, they are shock waves, but it's literally massive, huge neutron and black hole sized transmissions of basically it going thump, 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 as it comes around in a circle. It's crazy, but it's light. It's actually in a light wave, but so strong. It's literally a radio transmission with a low frequency, but very, very strong, where it's literally shaking atoms a tiny little bit, 100 million years, 200 million years later, going through space. Something to think about.